Hello. All right. So, last time we started talking about overfitting and regularization. We covered overfitting. It didn't involve much new code. There wasn't much for us to implement. Basically just learned that you have to make sure the training data is representative of the validation and testing data, otherwise you're going to overfit for the training data. The one thing we did implement is the early stopping criteria. So what it's trying to do is, if you can see that you're not learning anymore, stop. But it doesn't really work very well, so I've got it commented out. And now let's move on to regularization. Increasing the amount of training data is one way of reducing overfitting. Are there other ways we can reduce the extent to which overfitting occurs? One possible approach is to reduce the size of our network. However, large networks have the potential to be more powerful than small networks, and so this is an option we'd only adopt reluctantly. Fortunately, there are other techniques which can reduce overfitting. Even when we have a fixed network and fixed training data, these are known as regularization techniques. In this section, I describe one of the most commonly used regularization techniques, a technique sometimes known as weight decay or L2 regularization. The idea of L2 regularization is to add an extra term to the cost function, a term called the regularization term. Here's the regularized cross entropy. So this thing on the left is the cross entropy, and this thing on the right is, I'm guessing, the regularization term. The first term is just the usual expression for the cross entropy, but we've added a second term, namely the sum of the squares of all the weights in the network. This is scaled by a factor lambda over 2n, where lambda greater than 0 is known as the regularization parameter, and n is, as usual, the size of our training set. I'll discuss later how lambda is chosen. It's also worth noting that the regularization term doesn't include the biases. I'll also come back to that below. Of course, it's possible to regularize other cost functions, such as the quadratic cost. This can be done in a similar way. So the left side is the quadratic cost, right side is the regularization term. Is that what it's called? Regularization term. In both cases, we can write the regularized cost function as C0 plus regularization term, where C0 is the original unregularized cost function. Intuitively, the effect of regularization is to make it so the network prefers to learn small weights, all other things being equal. Large weights will only be allowed if they considerably improve the first part of the cost function. Put another way, regularization can be viewed as a way of compromising between finding small weights and minimizing the original cost function. The relative importance of the two elements of the compromise depends on the value of lambda. When lambda is small, we prefer to minimize the original cost function, but when lambda is large, we prefer small weights. When lambda is small, we prefer to minimize the original cost function. But when lambda is large, we prefer small weights. Got it, okay. Because we're trying to minimize this whole thing. So if lambda is large, minimizing this whole thing will mean minimizing this. Now, it's really not at all obvious why making this kind of compromise should help reduce overfitting, but it turns out that it does. We'll address the question of why it helps in the next section, but first let's work through an example showing that regularization really does reduce overfitting. So I already know why regularization is so powerful. It's because you're forcing the network to only learn helpful stuff. So any weight that's not doing helpful work is contributing to the cost without giving a benefit, and any weight that's actually helping you classify is contributing to the cost with a benefit. So you're going to get rid of all the excess fat. You're going to get rid of everything that's there but that's not helping. Okay. To construct such an example, we first need to figure out how to apply our stochastic gradient descent learning algorithm in a regularized neural network. In particular, we need to know how to compute the partial derivatives, derivative of c with respect to w, and derivative of c with respect to b for all the weights and biases in the network. Taking the partial derivatives of equation 87 gives us derivative of c with respect to w is equal to derivative of c0 with respect to w plus lambda over n w. Yeah, it does. I could have figured that out. So you've got this regularization term. We want, here, let's see if I can just do it. So, I think the back propagation stays the same that it is, because this is going to give us the or here, let me say it like this. Derivative of c with respect to w is going to be equal to derivative of c0 with respect to w plus derivative of this thing with respect to w. Derivative of this thing with respect to w is going to be 2. You take the 2, you put it in the front. That cancels out with that 2. So lambda over n. And then I guess at this point you have to talk about which w you're talking about. So all of the w's that are not the w you're talking about go away. And so this stops being a sum and it starts being just a lambda w divided by n, where the w is the one with all the indices, w, l, j, k. So that means basically the derivative just includes w. So this would just be like this plus w. So self dot weights of I, because it's w for each of the indices in the matrix, and this is a whole matrix of them. And then derivative with respect to b, the weights don't come into play for b. As in, these are all constants, so b is the same as it was before. So I guess I'm saying I've just implemented L2 regularization. We could try and see if I'm right. It seems like that wasn't enough, but let's see. No, this is bad at learning now. If I didn't have this term, then it would be great at learning. Okay. Wait. I just said W, but you need a lambda and you need an N. Forgot about that. So, I don't know what a good choice of lambda is, so I'm just going to do 0.01. And we're going to vary it. And that's times this, and then we need to divide by n. I think in this case I can divide by m, because if I divide each mini batch by the number of them, then in the end I'll have divided by n. Because you sum up all the m's and you're going to get n in the end. So why don't we try that, and then why don't we try changing lambda to be different numbers. So already that works great, but that might just be because my lambda is so small that this extra term is not contributing. That's what I'm guessing. So let's kill that and make lambda bigger. Very hard to tell. I mean, this looks like it's a little bit worse than before. So I'm guessing if I make it even bigger, that's going to make it even worse. Yeah. So 0. What if I make it even smaller than the first try? The problem is at this point it's getting so small that it might not be doing anything anymore. Yeah, it's very hard to tell if it's doing anything. And then what if I make it somewhere in between, 0.05? Yeah, I basically can't tell if it's doing anything. So let's keep reading and see if this is even the right way to do it. All right, so these are the two equations that we peaked at, and then we went back and derived ourselves. The derivative of C0 with respect to W and C0 with respect to B terms can be computed using backpropagation as described in the last chapter, and we see that it's easy to compute the gradient of the regularized cost function. Just use backpropagation as usual, and then add lambda over n W to the partial derivative of all the weight terms. The partial derivative with respect to the biases are unchanged, and so the gradient descent learning rule for the biases doesn't change from the usual rule, which is B goes to B minus eta times derivative of C0 times B, or with respect to B. The learning rule for the weights becomes W goes to W minus eta times derivative of C with respect C0 with respect to W minus eta lambda over n W. And I think that's what I was doing. Although, actually, I guess I shouldn't have this over m here because I've got the over m here already. If I'm doing it this way. As in, if I'm putting it inside the grad W instead of outside into here. Then you have the eta. You have the eta, you have the over m, and you have the lambda, which is right here, and the w, which is right here. So this isn't worth trying because this is the same as varying my lambda for my example, which I already couldn't tell if it was doing anything. This is exactly the same as the usual gradient descent learning rule, except we first rescale the weight w by a factor 1 minus eta lambda over n. This rescaling is sometimes referred to as weight decay, since it makes the weights smaller. At first glance, it looks as though this means the weights are being driven unstoppably towards zero, but that's not right, since the other term may lead the weights to increase, if so doing causes a decrease in the unregularized cost function. So I guess this is a different way to think about it, is that instead of changing the gradient, you're making the weights smaller and then you're updating in the direction of the gradient. Okay, that's how gradient descent works. What about stochastic gradient descent? Well, just as in unregularized stochastic gradient descent, we can estimate derivative of C0 with respect to W by averaging over a mini batch of M training examples. Thus, the regularized learning rule for stochastic gradient descent becomes CF equation 20. W goes to scaled W minus eta over M times the sum of the derivatives of the cost function with respect to W, where the sum is over training examples X in the mini batch and Cx is the unregularized cost for each training example. This is exactly the same as the usual rule for stochastic gradient descent, except the 1 minus eta lambda over n weight decay factor. Finally, for completeness, let me state the regularized learning rule for the biases. That is, of course, exactly the same as in the unregularized case, CF equation 21. Where the sum is over the training examples X in the mini batch. Let's see how regularization changes the performance of our neural network. We'll use a network with 30 hidden neurons. Okay, maybe, yeah, so that's what I have. A mini batch size of 10, okay. A learning rate of 0.5, so that's that. A cross entropy function, so that would be this. And a lambda of 0.1. So I just want to see if my implementation has a chance here with the other hyperparameters set the way that the book says to set them. No, this isn't really working. I wonder why. So I could do it the way they're saying to do it, where you just rescale W, but I don't know why what I'm doing doesn't work. Why shouldn't that be equivalent to what I'm doing? I would think it should be. I've also used the test data again, not the validation data. Strictly speaking, we should use the validation data for all the reasons we discussed earlier, but I decided to use the test data because it makes the results more directly comparable with our earlier unregularized results. You can easily change the code to use the validation data instead, and you'll find it gives similar results. The cost on the training data decreases over the whole time, much as it did in the earlier unregularized case. And this and the next two graphs were produced with the program overfitting.py. But this time the accuracy on the test data continues to increase for the entire 400 epochs. Wait, 400 epochs? I missed that part. "400 epochs. Oh, okay. 400 epochs and a very small training data. So this is the thing that had trouble learning anything before. So maybe regularization helps with this. You know what? I actually don't remember what this used to do, so, oops. What did you used to do before I had this? So you slowly go up to 80 and then you get stuck. You get stuck at 81. 82. What am I printing right here? I'm printing the... Here, test data. I'm validating against test data and I'm printing this. So I get stuck at 82% on test data, and presumably I get to 100% on training data. Okay, so let's kill that, and let's add regularization. And now the deal is we're not supposed to get stuck at 81. We're supposed to keep learning the whole time. We're bouncing around a lot. We're higher than 81, mostly. I don't know if that's... I don't know if we're seeing what we're supposed to be seeing. This doesn't really look that good. And I guess in his example, he gets up to 87. Although I guess we did bounce around 87. And we are bouncing around a lot, kind of like this. But no, he's from 200 to 400, he's above 86 the whole time. That could be random though. Okay, very hard to tell if I did it right. I guess we'll just have to keep reading and then compare our implementations. Clearly the use of regularization has suppressed overfitting. What's more, the accuracy is considerably higher, with a peak classification accuracy of 87.1% compared to the peak of 82.2% obtained in the unregularized case. Yeah, I guess my peak was higher also. I got 85.28 at the end, and without the regularization, I kind of get stuck at 81. It's a lot more well-behaved, but I don't think it gets higher than 81. So I think I am seeing the same thing that he's seeing. Okay, what happens if we move out of the artificial environment of just having 1,000 training images and return the full 50,000 image training set? Of course, we've seen already that overfitting is much less of a problem with the full 50,000 images. Does regularization help any further? Let's keep the hyperparameters the same as before. 30 epochs. 30 epochs. Learning rate of 0.5. Batch size of 10. However, we need to modify the regularization parameter. The reason is because the size n of the training set has changed from n equals 1,000 to n equals 50,000. And this changes the weight decay factor 1 over eta lambda over n. Or sorry, 1 minus eta lambda over n. If we continued to use lambda equals 0.1, that would mean much less weight decay and thus much less of a regularization effect. We compensate by changing to lambda equals 5.0. Okay, so let's go over here. I guess let's just remind ourselves how it behaves when we don't have regularization, and I think the answer is it starts around 90, 91, and it goes up to 95. Oh. Wait, I'm not using... I forgot to use the full training set. Okay, starts at 91. And then it's going to take 30 seconds to get us around 95. Now 5.0 is the factor that they're saying to use here. All right, we get it. It gets to around 95. And then with the regularization, with the huge lambda, it doesn't work at all. It doesn't work at all. It does this thing where it gets to like 9.8%, and that seems to happen. I mean, it used to happen whenever there were overflows. This time I don't know what the deal is because it didn't print that there were any overflows, but that's what happens when something is messed up. So I don't know. Let's see what they say. Okay, let's train our network. Stopping first to reinitialize the weights. So for them, it just worked properly. For me, it didn't work at all. And if I don't have this term, it works fine. That's so weird. When I make the term smaller, it starts working again. I guess that's what you would expect if I did this wrong and this thing is not helping. Like if it's actively harming, then that I'm not able to learn when it's there, and I start getting just 1 in 10 correct. I mean, here's what I can try to do. And I don't know why this would be any different, but let's regularize the way that they were saying to do it. So your times equal to like 1 minus lambda times eta over m. So you scale yourself and then you update based on the way it was before. Yeah, okay. So that's kind of the same. I mean, at least that means I'm not crazy. That it gives the same result as if I did that. And if I start scaling down lambda, does it behave the same way as before? Yeah, it does. So I'm still probably doing something wrong, but at least my confusion is not between the two different ways of thinking about rescaling, either as a change to grad W versus a scale of the weights. So I'm doing something wrong. I'm not getting the same results. I'm gonna have to look at his code and see what I'm doing wrong. So let's just keep reading for now. There's a lot of good news here. First, our classification accuracy on the test data is up from 95.49% when running unregularized to 96.49%. That's a big improvement. Second, we can see that the gap between results on the training data and the test data is much narrower than before, running at under 1%. That's still a significant gap, but we've obviously made substantial progress reducing overfitting. Finally, let's see what test classification accuracy we get when we use 100 hidden neurons and a regularization parameter of lambda equals 5.0. I won't go through a detailed analysis of overfitting here. This is purely for fun, just to see how high an accuracy we can get when we use our new tricks. The cross-entropy cost function in L2 regularization, and then they do it. The final result is a classification accuracy of 97.92% on the validation data. That's a big jump from the 30 hidden neuron case. In fact, tuning just a little more to run for 60 epochs at eta equals 0.1 and lambda equals 5.0, we break the 98% barrier, achieving 98.04% classification accuracy on the validation data. Not bad for what turns out to be 152 lines of code. I've described regularization as a way to reduce overfitting and to increase classification accuracies. In fact, that's not the only benefit. Empirically, when doing multiple runs of our MNIST networks, but with different random weight initializations, I've found that the unregularized runs will occasionally get stuck, apparently caught in local minima of the cost function. The result is that different runs sometimes provide different results. By contrast, the regularized runs have provided much more easily replicable results. What is going on? Why is this going on? Heuristically, if the cost function is unregularized, then the length of the weight vector is likely to grow, all other things being equal. Over time, this can lead to the weight vector being very large indeed. This can cause the weight vector to get stuck pointing in more or less the same direction, since changes due to the gradient descent only make tiny changes to the direction when the length is long. I believe this phenomenon is making it hard for a learning algorithm to properly explore the weight space and consequently harder to find good minima of the cost function. So I don't want to move on yet until I have implemented regularization properly. Let's start by just looking at the equations and seeing if I'm missing something. Show me the one with M here. So W goes to 1 minus eta times lambda divided by n. Oh, what? You divide by the full length of the training data each time for each mini batch update? Interesting. I don't even have that in my context here. And it's weird that you wouldn't just define lambda as like you've already divided n. Okay, well, if this needs to be n, then I have to get n from somewhere. So you have to pass me n. You don't know what n is. N is len of training data. Does this do anything? Aha! Wait, am I using it? I am. So we should get to like 97%, hopefully. Or no, it was only 96. It got to 97 once you have 100 neurons. We didn't even get to 96. Let's try it one more time. Why don't we get to 96? Oh, we got to 90. Well, okay, we did get to 96 in the end. Again, it's really hard to tell the difference. I could do the thing where I try to do 100 neurons, which should get to 97, right? But how high does it get before regularization? Wait, we're if you run for 60 epochs at eta equals 0.1. Oh, we're getting the 97 with 100 neurons, but I don't remember what you're supposed to get if you don't have regularization. Look at that, 97.62%. 97.82. That's great. And then if I was not regularizing, so that would just be comment this line out. So we don't get up to 97. It's a difference of 1%. So I think we can finally conclude that regularization is working and helping. So this is L2 regularization. Let's clean up a little bit of this. So lambda obviously needs to be a parameter. So let's just do that. Lambda. So eta lambda n. Update mini batch. You have to pass lambda now. Is that the right order? Eta lambda n, yep. Which means you need to know about lambda. Which means you have to pass in lambda. Great. All right. Moving on. Why does regularization help reduce overfitting? We've seen empirically that regularization helps reduce overfitting. That's encouraging, but unfortunately it's not obvious why regularization helps. It's obvious to me, it's because you're trimming the fat. You're getting rid of stuff. You're getting rid of parts of your circuit that is not helping you predict. Which means you're only going to be learning useful stuff, which means you have more capacity to learn because you've wasted less of your weights on stuff that's not helpful. A standard story people tell to explain what's going on is along the following lines. Smaller weights are in some sense lower complexity and so provide a simpler and more powerful explanation for the data and should thus be preferred. That's a pretty terse story, though, and contains several elements that perhaps seem dubious or mystifying. Let's unpack the story to examine it critically. To do that, let's suppose we have a simple dataset for which we wish to build a model. Implicitly, we're studying some real-world phenomenon here, with X and Y representing real-world data. Our goal is to build a model which lets us predict y as a function of x. We could try using neural networks to build such a model, but I'm going to do something even simpler. I'll try to model y as a polynomial in x. I'm doing this instead of using neural nets because using polynomials will make things particularly transparent. Once we've understood the polynomial case, we'll translate to neural networks. Now there are 10 points in the graph above, which means we can find a unique ninth order polynomial y equals a0 x to the 9 plus a1 x to the 8 plus etc. plus a9, which fits the data exactly. Here's the graph of that polynomial. Footnote. I won't show the coefficients explicitly, although there are easy to find routines such as NumPy's polyfit. You can view the exact form of the polynomial in the source code of the graph if you're curious. It's the function p of x defined starting on the line 14 of the program, which produces the graph. Okay. Here's the graph of the 9 coefficient polynomial, 9th degree polynomial, that provides an exact fit. But we can also get a good fit using the linear model y equals 2x. Yeah, so you can do a straight line right through it, or you can have a polynomial that is exactly right on each of the points, but does crazy, unpredictable stuff between them. Which of these is the better model? Which is more likely to be true, and which model is more likely to generalize well to other examples of the same underlying real-world phenomenon? These are difficult questions. In fact, we can't determine with certainty the answer to any of the above questions without much more information about the underlying real-world phenomenon. But let's consider two possibilities. One, the ninth order polynomial is in fact the model which truly describes the real-world phenomenon, and the model will therefore generalize perfectly. And two, the correct model is y equals 2x, but there's a little additional noise due to, say, measurement error, and that's why the model isn't an exact fit. It's not a priori possible to say which of these two possibilities is correct, or indeed if some third possibility holds. Logically, either could be true, and it's not a trivial difference. It's true that on the data provided, there's only a small difference between the two models. But suppose we want to predict the value of y corresponding to some large value of x, much larger than any shown in the graph above. If we try to do that, there will be a dramatic difference between the predictions of the two models, as the ninth order polynomial comes to be dominated by the x to the 9th term, while the linear model remains well linear. One point of view is to say that in science we should go with the simpler explanation unless compelled not to. When we find such a model that seems to explain many data points, we are tempted to shout "Eureka!" After all, it seems unlikely that a simple explanation should occur merely by coincidence. Rather, we suspect that the model must be expressing some underlying truth about the phenomenon. In the case at hand, the model y equals 2x plus noise seems much simpler than y equals a0 to x times x to the 9 plus a1 times x to the 8 plus etc. It would be surprising if that simplicity had occurred by chance, and so we suspect that y equals 2x plus noise expresses some underlying truth. In this point of view, the ninth order model is really just learning the effects of local noise, and while the ninth order model works perfectly for these particular data points, the model will fail to generalize to other data points, and the noisy model will have the noisy linear model will have greater predictive power. Let's see what this point of view means for neural networks. Suppose our network mostly has small weights, as will tend to happen in regularized networks. The smallness of the weights means that the behavior of the network won't change too much if we change a few random inputs here and there. That makes it difficult for a regularized network to learn the effects of local noise in the data. Think of it as a way of making it so single pieces of evidence won't matter too much to the output of the network. Instead, a regularized network learns to respond to types of evidence which are seen often across the training set. By contrast, a network with large weights may change its behavior quite a bit in response to small changes in the input. And so unregularized networks can use large weights to learn a complex model that carries a lot of information about the noise in the training data. In a nutshell, regularized networks are constrained to build relatively simple models based on the patterns seen often in the training data, and are resistant to learning peculiarities of the noise of the training data. The hope is that this will force our networks to do real learning about the phenomenon at hand and generalize better from what they learn. With that said, the idea of preferring simpler explanations should make you nervous. People sometimes refer to this idea as Occam's razor and will zealously apply it as though it has the status of some general scientific principle. But of course, it's not a general scientific principle. There's no a priori logical reason to prefer simple explanations over more complex explanations. Indeed, sometimes the more complex explanation turns out to be correct. Let me describe two examples where more complex explanations have turned out to be correct. In the 1940s, physicist Marcel Schein announced the discovery of a new particle of nature. The company he worked for, General Electric, was ecstatic and publicly publicized the discovery widely, but the physicist Hans Bethe was skeptical. Bethe visited Schein and looked at the plates showing the tracks of Schein's new particle. Schein showed Bethe plate after plate, but on each plate Bethe identified some problem that suggested the data should be discarded. Finally, Schein showed Bethe a plate that looked good. Bethe said it might just be a statistical fluke. Schein: yes, but the chance that this would be statistics, even according to your own formula, is 1 in 5. Bethe: but we have already looked at 5 plates. Finally, Schein said, but on my plates, each one of the good plates, each one of the good pictures, you explain by a different theory, whereas I have one hypothesis that explains all the plates, that they are the new particle. Bethe replied, the sole difference between your and my explanations is that yours is wrong and all of mine are right. Your single explanation is wrong and all of my multiple explanations are right. Subsequent work confirmed that nature agreed with Bethe and Schein's particle is no more. Footnote: this story is related by the physicist Richard Feynman in an interview with the historian Charles Wiener. As a second example, in 1859, the astronomer Urbain Le Verrier observed that the orbit of the planet Mercury doesn't have quite the shape that Newton's theory of gravitation says it should have. It was a tiny, tiny deviation from Newton's theory, and several of the explanations proffered at the time boiled down to saying that Newton's theory was more or less right, but needed a tiny alteration. In 1916, Einstein showed that the deviation should be explained very well using his general theory of relativity, a theory radically different to Newtonian gravitation and based on much more complex mathematics. Despite the additional complexity, today it's accepted that Einstein's explanation is correct, and Newtonian gravity, even in its more general forms, is wrong. This is in part because we now know that Einstein's theory explains many other phenomena which Newton's theory has difficulty with. Furthermore, even more impressively, Einstein's theory accurately predicts several phenomena which aren't predicted by Newtonian gravity at all. These impressive qualities weren't entirely obvious in the early days. If one had judged merely on the grounds of simplicity, then some modified form of Newton's theory would arguably have been more attractive. There are 3 morals to draw from these stories. First, it can be quite a subtle business deciding which of 2 explanations is truly simpler. Second, even if we can make such a judgment, simplicity is a guide that must be used with great caution. Third, the true test of a model is not its simplicity, but rather how well it does in predicting new phenomenon in new regimes of behavior. With that said, and keeping the need for caution in mind, it's an empirical fact that regularized networks usually generalize better than unregularized networks, and so through the remainder of this book, we will make frequent use of regularization. I've included the stories above merely to help convey why no one has yet developed an entirely convincing theoretical explanation of why regularization helps networks generalize. Indeed, researchers continue to write papers where they try different approaches to regularization, compare them to see which works better, and attempt to understand why different approaches work better or worse. And so you can view regularization as something of a kludge. While it often helps, we don't have an entirely satisfactory systemic understanding of what's going on, merely incomplete heuristics and rules of thumb. There's a deeper set of issues here. Issues which go to the heart of science. It's a question of how we generalize. Regularization may give us a computational magic wand that helps our networks generalize better, but it doesn't give us principled understanding of how the generalization works, nor of what the best approach is. Footnote: these issues go back to the problem of induction, famously discussed by the Scottish philosopher David Hume in An Inquiry Concerning Human Understanding, 1748. The problem of induction has been given a modern machine learning form in the no free lunch theorem of David Wolpert and William Macready. This is particularly galling because in everyday life we generalize phenomenally well. Shown just a few images of an elephant, a child will quickly learn to recognize other elephants. Of course, they may occasionally make mistakes, perhaps confusing a rhinoceros for an elephant, but in general this process works remarkably accurately. So we have a system, the human brain, with a huge number of free parameters, and after being shown just one or a few training images, that system learns to generalize to other images. Our brains are, in some sense, regularizing amazingly well. How do we do it? At this point, we don't know. I expect that in years to come, we will develop more powerful techniques for regularization in artificial neural networks. techniques that will ultimately enable neural nets to generalize well, even from small data sets. Has that happened? What's the best regularization method in neural networks? Dropout and L2 regularization. So I guess we haven't developed new techniques. L1, L2, and dropout are most common. Okay. In fact, our networks already generalize better than one might a priori expect. A network with 100 hidden neurons has nearly 80,000 parameters. We have only 50,000 images in our training data. It's like trying to fit an 80,000th degree polynomial to a 50,000 data points. By all rights, our networks should overfit terribly, and yet, as we saw earlier, such a network actually does a pretty good job of generalizing. Why is that the case? It's not well understood. It has been conjectured that the dynamics of gradient descent learning in multi-layer nets has a self-regularizing effect. This is exceptionally fortunate, but it's also somewhat disquieting that we don't understand why it's the case. In the meantime, we will adopt the pragmatic approach and use regularization whenever we can. Our neural networks will be better for it. Footnote: in gradient-based learning applied to document recognition by Yann LeCun, Léon Bottou, Yoshua Bengio, and Patrick Hafner, 1998. Let me conclude this section by returning to a detail which I left unexplained earlier, the fact that L2 regularization doesn't constrain the biases. Of course, it would be easy to modify the regularization procedure to regularize the biases. Empirically, doing this often doesn't change the results very much. So to some extent, it's merely a convention whether to regularize the biases or not. However, it's worth noting that having a large bias doesn't make a neuron sensitive to inputs in the same way as having large weights. And so we don't need to worry about large biases enabling our network to learn noise in our training data. At the same time, allowing large biases gives our networks more flexibility in behavior. In particular, large biases make it easier for neurons to saturate, which is sometimes desirable. For these reasons, we don't usually include a bias term when regularizing. So I wonder if I did it, if I would see no difference or if I would see it get worse. Because I can just do it, right? I can just say biases is, yeah, now they're just regularizing same as before, or same as weights. And what do you see if you do that? It still works. I don't think I can tell the difference between regularizing the biases and not regularizing the biases. But you would think from his explanation that it should get worse because now it's harder for neurons to saturate, which is a desirable property. So 95.8, and then if we don't regularize the bias, I guess I did make it worse by regularizing the bias, I guess. Okay. Other techniques for regularization. There are many regularization techniques other than L2 regularization. In fact, so many techniques have been developed that I can't possibly summarize them all. In this section, I briefly describe 3 other approaches to reduce overfitting: L1 regularization, dropout, and artificially increasing the training set size. We won't go into nearly as much depth studying these techniques as we did earlier. Instead, the purpose is to get familiar with the main ideas and to appreciate something of the diversity of regularization techniques available. L1 regularization. In this approach, we modify the unregularized cost function by adding the sum of the absolute values of the weights. So we added the squares before. This time we're adding the absolute values. Intuitively, this is similar to L2 regularization, penalizing large weights and tending to make the network prefer small weights. Of course, the L1 regularization term isn't the same as the L2 regularization term, and so we shouldn't expect to get exactly the same behavior. Let's try to understand how the behavior of a network trained using L1 regularization differs from a network trained using L2 regularization. All right, and I can do this, right? So you, if you take the partial derivative of this whole thing of C with respect to B, it's the same as before, so it doesn't change. If you take the partial derivative with respect to C, or sorry, with respect to W, then this part's the same as before. And then you get the derivative of the absolute value of W, which is either the derivative of W or the derivative of negative W. That's just what absolute value means. Absolute value means W or negative W, depending on the sign of W. So, so the derivative of W is 1, and the derivative of negative W is -1. So this term is going to be either 1 or -1, depending on the sign of W. Which basically means you just do plus is there a Python thing for getting the sign of something? Python get sign of number. Math.copy sign. NumPy.sign. Okay, NumPy.sign. So I want sign of W, which is self.weights of I. So you're either a +1 or a -1. Is there a way, and then like, okay. And then how do you move that out of the grad so that you can do it on its own line like this? Oh, actually also, I need to keep track of my lambda and my n. This is hard to do all in my head. I think the basic thing is going to be, instead of rescaling weights by an amount proportional to W, we'll be adding like this to it. Lambda times eta times either +1s or -1s or 0, depending on the absolute value. Is this possible? Could this be how you do L1 regularization? Maybe. I mean, it didn't destroy the results. I guess our lambda, we have no idea what the right setting of lambda is. So I could keep reading and try to see how he sets his hyperparameters. Oh, sine of W, look at that. We actually predicted something. All right, to do that, we'll look at the partial derivatives of the cost function. Differentiating 95, we obtain derivative of c with respect to w equals derivative of c0 with respect to w plus lambda over n sine of w, where sine of w is the sine of w. That is plus 1 if w is positive, minus 1 if w is negative. Using this expression, we can easily modify backpropagation to do stochastic gradient descent using L1 regularization. The resulting update rule for an L1 regularized network is w goes to w prime, which is equal to w minus I guess my sign is wrong here, so but it is minus eta times lambda over n, eta times lambda over n times sine of the weights, and then minus the other stuff. So there it is. I almost had it. I just had the sign wrong in the end. Cool. Whereas per usual, we can estimate derivatives of C0 with respect to W using a mini batch average if we wish. Compare that to the update rule for L2 regularization, which was that. In both expressions, the effect of regularization is to shrink the weights. This accords with our intuition that both kinds of regularization penalize large weights. But the way the weights shrink is different. In L1 regularization, the weights shrink by a constant amount towards 0. In L2 regularization, the weights shrink by an amount which is proportional to W. And so when a particular weight has a large magnitude, absolute value of W, L1 regularization shrinks the weight much less than L2 regularization does. By contrast, when absolute value of W is small, L1 regularization shrinks the weight much more than L2 regularization. The net result is that L1 regularization tends to concentrate the weight of the network in a relatively small number of high importance connections, while the other weights are driven towards 0. I've glossed over an issue in the above discussion, which is that the partial derivative of c with respect to w isn't defined when w equals 0. The reason is that the function absolute value of w has a sharp corner at w equals 0, and so it's not differentiable at that point. That's okay though. What we'll do is just apply the usual unregularized rule for stochastic gradient descent when w equals 0. That should be okay. Intuitively, the effect of regularization is to shrink weights, and obviously it can't shrink a weight which is already 0. To put it more precisely, we'll use equations 96 and 97 with the convention that sine of 0 equals 0. That gives a nice compact rule for doing stochastic gradient descent with L1 regularization. Cool. Cool beans. And there we go, L1 regularization. Dropout. Dropout is a radically different technique for regularization. Unlike L1 and L2 regularization, dropout doesn't rely on modifying the cost function. Instead, in dropout, we modify the network itself. Let me describe the basic mechanics of how dropout works before getting into why it works and what the results are. Suppose we're trying to train a network. In particular, suppose we have a training input x and a corresponding desired output y. Ordinarily, we'd train by forward propagating x through the network and then back propagating to determine the contribution to the gradient. With dropout, this process is modified. We start by randomly and temporarily deleting half the hidden neurons in the network, while leaving the input and output neurons untouched. After doing this, we'll end up with a network along the following lines. Note that the dropout neurons, i.e. the neurons which have been temporarily deleted, are still ghosted in. Okay, temporarily delete some neurons. Delete half the hidden neurons. We forward propagate the input x through the modified network and then back propagate the result, also through the modified network. After doing this over a mini batch of examples, we update the appropriate weights and biases We then repeat the process, first restoring the dropout neurons, then choosing a new random subset of hidden neurons to delete, estimating the gradient for a different mini-batch, and updating the weights and biases in the network. By repeating this process over and over, our network will learn a set of weights and biases. Of course, those weights and biases will have been learnt under conditions in which half the neurons were dropped out. When we actually run the full network, that means twice as many hidden neurons will be active. To compensate for that, we have the weights outgoing from the hidden neurons. This dropout procedure may seem strange and ad hoc. Why would we expect it to help with regularization? To explain what's going on, I'd like you to briefly stop thinking about dropout and instead imagine training neural networks in the standard way, no dropout. In particular, imagine we trained several different neural networks, all using the same training data. Of course, the networks may not start out identical, and as a result, after training, they may sometimes give different results. When that happens, we could use some kind of averaging or voting scheme to decide which output to accept. For instance, if we have trained 5 networks and 3 of them are classifying a digit as a 3, then it probably really is a 3. This reminds me of something called mixture of experts, which is what ChatGPT uses. But I don't actually know how that works. I've just heard the name and a layman's description. The other 2 networks are probably just making a mistake. This kind of averaging scheme is often found to be a powerful, though expensive, way of reducing overfitting. The reason is that the different networks may overfit in different ways, and averaging may help eliminate that kind of overfitting. What's this got to do with dropout? Heuristically, when we drop out different sets of neurons, it's rather like we're training different neural networks, and so the dropout procedure is like averaging the effects of a very large number of different networks. The different networks will overfit in different ways, and so hopefully the net effect of dropout will be to help reduce overfitting. A related heuristic explanation for dropout is given in one of the earliest papers to use this technique. Footnote: ImageNet Classification with Deep Convolutional Neural Networks by Alex Krzyzewski, Ilya Sutskever, and Jeffrey Hinton, 2012. This technique reduces complex co-adaptations of neurons, since a neuron cannot rely on the presence of particular other neurons. It is therefore forced to learn more robust features that are useful in conjunction with many different random subsets of other neurons. In other words, if we think of our network as a model which is making predictions, we can think of dropout as a way of making sure that the model is robust to the loss of any individual piece of evidence. In this, it's somewhat similar to L1 and L2 regularization, which tend to reduce weights and thus make the network more robust to losing any individual connection in the network. I'm not sure how L1 and L2 make you more robust to losing any individual connection in the network. I guess that's not my intuition. I would think, if anything, it makes you less robust to that because you have less weights. So you're going to be learning a more how do I say this? Like, you're gonna you're learning like a more tight rule, if that makes sense. Like you can't really have redundancy because you're penalized by you're penalizing having weights. So I guess I would expect that you would have less redundancy, which would make you less robust to losing stuff. But I don't know. Anyway, I kind of get why dropout should make sense. It's like you're not allowing the neurons to learn. You're forcing them to be redundant. You're not allowing them to get stuck in any kind of way. So like they have to learn to recognize a 3 even if half of their brain is off. So they have to like really learn to recognize a 3. Of course, the true measure of dropout is that it has been very successful in improving the performance of neural networks. The original paper introducing the technique applied it to many different tasks. For us, it's of particular interest that they applied dropout to MNIST digit classification using a vanilla feed-forward neural network along lines similar to those we've been considering. The paper noted that the best result anyone had achieved up to that point using such an architecture was 98.4% classification accuracy on the test set. They improved that to 98.7% accuracy using a combination of dropout and a modified form of L2 regularization. Similarly impressive results have been obtained for many other tasks, including problems in image and speech recognition and natural language processing. Dropout has been especially useful in training large, deep neural networks where the problem of overfitting is often acute. Okay, so dropout's going to be a lot harder for me to implement here. I actually don't even know how I would do it. Actually, I think I know how I would do it. It's just that I would have to replace all of the weights and biases with matrices half their size. Do a forward propagation, do a backwards propagation, and then scale those matrices back up. Those gradient, the grad matrices back up. Remember all of the weights that are missing, and like turn it back into a matrix that's twice the size, with a bunch of zeros in half the places. Well, more than half the places for the weights, half the places for the biases. And then use that to update my weights and biases. But that sounds hard to do. I think, why don't we finish this chapter and then decide if we want to do that. So I'm just going to put a to do. I don't know where to put it. Why don't I put it out here? To do implement dropout regularization. Okay. Artificially expanding the training data. We saw earlier that our MNIST classification accuracy dropped down to percentages in the mid-80s when we used only 1,000 training images. It's not surprising that in this case, this is the case, since less training data means our network will be exposed to fewer variations in the way human beings write digits. Let's try training our 30 hidden neuron with a variety of different training data set sizes to see how performance varies. We train using a mini batch size of 10, a learning rate eta equals 0.5, a regularization parameter lambda equals 5.0, and the cross entropy cost function. We will train for 30 epochs when the full training dataset is used, and scale up the number of epochs proportionally when smaller training sets are used. To ensure the weight decay factor remains the same across training sets, we will use a regularization parameter of lambda equals 5.0 when the full training dataset is used, and scale down lambda proportionally when smaller training sets are used. Footnote, this and the next two graphs are produced with the program moredata.py. Okay, so training set size, as it goes up, accuracy goes up, and it has this weird shape where it wants to be, where it goes up really fast at first and then plateaus. As you can see, the classification accuracies improve considerably as we use more training data. Presumably, this improvement would continue still further if more data was available. Of course, looking at the graph above, it does appear that we're getting near saturation. Suppose, however, that we redo the graph with the training set size plotted logarithmically. Okay. it's the same effect, but a little more flat, a little more linear, I mean. It seems that the graph is still going up towards the end. This suggests that if we used vastly more training data, say millions or even billions of handwriting samples instead of just 50,000, then we'd likely get considerably better performance even from this very small network. Obtaining more training data is a great idea. Unfortunately, it can be expensive, so it is not always possible in practice. However, there's another idea which can work nearly as well, and that's to artificially expand the training data. Suppose, for example, that we take an MNIST training image of a 5 and rotate it by a small amount, say 15 degrees. It's still recognizably the same digit, and yet at the pixel level, it's quite different to any image currently in the MNIST training data. It's conceivable that adding this image to the training data might help our network learn more about how to classify digits. What's more, obviously, we're not limited to adding just this one image. We can expand our training data by making many small rotations of all the MNIST training images and then using the expanded training data to improve our network's performance. This idea is very powerful and has been widely used. Let's look at some of the results from a paper. Footnote. Best practices for convolutional neural networks applied to visual document analysis by Patrice Simard, David Steinkraus, and John Platt, 2003. Which applied several variations of the idea to MNIST. One of the neural network architectures they considered was along similar lines to what we've been using, a feed-forward network with 800 hidden neurons and using the cross-entropy cost function. Running the network with the standard MNIST training data, they achieved a classification accuracy of 98.4% on their test set. But then they expanded the training data using not just rotations as I described above, but also translating and skewing the images. By training on the expanded dataset, they increased the network's accuracy to 98.9%. They also experimented with what they called elastic distortions, a special type of image distortion intended to emulate the random oscillations found in hand muscles. By using the elastic distortions to expand the data, they achieved an even higher accuracy, 99.3%. Effectively, they were broadening the experience of their network by exposing it to the sort of variations that are found in real handwriting. Variations on this idea can be used to improve performance on many learning tasks, not just handwriting recognition. The general principle is to expand the training data by applying operations that reflect real-world variation. It's not difficult to think of ways of doing this. Suppose, for example, that you're building a neural network to do speech recognition. We humans can recognize speech even in the presence of distortions such as background noise. And so you can expand your data by adding background noise. We can also recognize speech if it's sped up or slowed down, so that's another way we can expand the training data. These techniques are not always used. For instance, instead of expanding the training data by adding noise, it may well be more efficient to clean up the input to the network by first applying a noise reduction filter. Still, it's worth keeping the idea of expanding the training data in mind and looking for opportunities to apply it. Alright, then we've got exercises. So I'm not gonna do this thing of changing the training data because my goal is to write a large language model, and so I would just be taking too big of a detour by doing stuff that only applies to image recognition. However, the dropout thing, that's just a basic neural network thing, so we might do that. Exercise. As discussed above, one way of expanding the MNIST training data is to use small rotations of training images. What's a problem that might occur if we allow arbitrarily large rotation of training images? Okay, so obviously 9 and 6 become indistinguishable if you can rotate all the way around. An aside on big data and what it means to compare classification accuracies. Let's look again at how our neural network's accuracy varies with training set size. Suppose that instead of using a neural network, we use some other machine learning technique to classify digits. For instance, let's try using the support vector machines, SVM, which we met briefly back in Chapter 1. As was the case in Chapter 1, don't worry if you're not familiar with SVMs, we don't need to understand their details, instead we'll use the SVM supplied by the scikit-learn library. Here's how SVM performance varies as a function of training set size. I've plotted the neural net results as well to make a comparison easy. Okay. So neural network accuracy is the one above, SVM accuracy is the one below. They scale similarly, although neural network accuracy is always above SVM accuracy. Probably the first thing that strikes you about this graph is that our neural network outperforms the SVM for every training set size. That's nice, although you shouldn't read too much into it, since I just used the out-of-the-box settings for the scikit-learn's SVM, while we've done a fair bit of work improving our neural network. A more subtle but more interesting fact about the graph is that if we train our SVM using 50,000 images, then it actually has better performance, 94.48% accuracy, than our neural network does when trained with 5,000 images, 93.24% accuracy. In other words, more training data can sometimes compensate for differences in the machine learning algorithm used. Something even more interesting can occur. Suppose we're trying to solve a problem using two machine learning algorithms, algorithm A and algorithm B. It sometimes happens that algorithm A will outperform algorithm B with one set of training data, while algorithm B will outperform algorithm A with a different set of training data. We don't see that above. It would require the two graphs to cross, but it does happen. Footnote. Striking examples may be found in scaling to very, very large corpora from natural language disambiguation by Michele Banco and Eric Brill, 2001. The correct response to the question, is algorithm A better than algorithm B, is really, what training data set are you using? All this is a caution to keep in mind, both when doing development and when reading research papers. Many papers focus on finding new tricks to wring out improved performance on standard benchmark datasets. Our whiz-bang technique gives us an improvement of X% on standard benchmark Y is a canonical form of a research claim. Such claims are often genuinely interesting, but they must be understood as applying only in the context of the specific training dataset used. Imagine an alternate history in which the people who originally created the benchmark dataset had a larger research grant. They might have used the extra money to collect more training data. It's entirely possible that the improvement due to the whiz-bang technique would disappear on a larger training data set. In other words, the purported improvements might just be an accident of history. The message to take away, especially in practical applications, is that what we want is both better algorithms and better training data. It's fine to look for better algorithms, but make sure you're not focusing on better algorithms to the exclusion of easy wins getting more or better training data. Problems, and this is a research problem, so this is not a real problem. This is a goodwill hunting problem. How do our machine learning algorithms perform in the limit of very large data sets? For any given algorithm, it's natural to attempt to define a notion of asymptotic performance in the limit of truly big data. A quick and dirty approach to this problem is to simply try fitting curves to graphs like those shown above, and then to extrapolate the fitted curves out to infinity. An objection to this approach is that different approaches to curve fitting will give you different notions of asymptotic performance. Can you find a principled justification for fitting to some particular class of curves? If so, compare the asymptotic performance of several different machine learning algorithms. Yeah, I mean, I guess it's like, if we look at these things, it's like, yeah, I guess I don't know how to say it better than you can kind of see the trend of the graph. I don't think I can come up with a principled approach for how to formalize what type of curve this is. And then the second part of the problem is try different machine learning algorithms and see how they compare. And I'm not going to be doing that either, but I actually don't even know any other machine learning algorithms, come to think of it, other than the ones we've been seeing, which is neural networks and SVMs. I guess there's like basic, what do you call it, regression, but that's, I think SVM is strictly better than that. Okay, summing up, we've now completed our dive into overfitting and regularization. Of course, we'll return again to the issue. As I've mentioned several times, overfitting is a major problem in neural networks, especially as computers get more powerful, and we have the ability to train larger networks. As a result, there's a pressing need to develop powerful regularization techniques to reduce overfitting, and this is an extremely active area of current work. Okay. Do I want to implement dropout regularization right now? So how would you do it? It would be something like, is it in each epoch, or how did they decide? Is it for each mini batch, or for each epoch that you get a new dropped out set of weights? For each mini batch. So you start by dropping out half the network, feed forward, back propagate, do this over a mini batch, update the weights and biases, and then restore the dropped out neurons. Okay. So for every mini batch, that means we can do the whole thing inside update mini batch. Backprop would actually, maybe we could do it all inside backprop also. So when you do the forward propagation, before you start, basically, you'd have to make a copy of the weights and biases. I'm trying to think of the right way to do this, because the thing I was thinking before was you choose which neurons will be dropped out. Then you make the weights and biases matrices to represent that network, so the network that doesn't have these hidden things. Then you do a forward propagation using that new network. Then you do a back propagation using that new network. Then you rebuild a matrix that's twice as big, or like more than twice as big, and you remember based on, like, I guess we would have had to remember which neurons are missing. Then we map the values from the small network to the big network. The values of the grad W's and the grad B's. That's how I was thinking of doing it. I'm trying to think if there's a way to do it where you basically just zero things out in matrices of the big size, and you never have to do a translation. You just kind of you start by just zeroing them out, and then you do forwards and backwards propagation normally, and then at the end you have your result. The problem is I'm gonna be assigning values to the zeros. I think that kind of works actually for the forward propagation, is I can just zero stuff out. And then for the backwards propagation, I think those two techniques would give different answers, but I'm not sure. Because for what I could do is just zero them out, forwards and backwards propagate, and then zero them out in the gradient, so that I don't actually learn that I should change the dropped out neurons, even though I would learn that. It's just that that's not going to give the same answer as if I actually backpropagated on a smaller network. Is it? It's hard to think about. How would I do it? So I've got my W. This would have to be W Hadamard product, a matrix of zeros and ones, so that I zero out the stuff I don't want. Same for B. And then in the backwards propagation, I would also multiply W and B by those. I guess you don't even use B in the backwards propagation. And then at the end, instead of returning, I would multiply by that masking matrix again, just to get rid of the contributions to dropped out neurons. The problem with this is that I'm gonna get a backpropagation that says, oh, what you really need to be doing here is increase the weights on a bunch of zeroed neurons. And then I'm gonna zero those out again at the end because I'm not trying to figure out what to do with those neurons right now. And that's gonna give a different answer than if I didn't consider those neurons at all, instead of considering them and then wiping them out. But the thing I can't picture in my head is it just a scaled up or scaled down version of the same answer, or is it going to be is it going to like totally not work because it's completely not the right way to do it? Maybe I could look up how to do dropout. Dropout in neural networks. Yeah, that's not what I'm looking for. I want to know, how do you actually do it? Oh. This sounds like the thing I was just describing. Google holds the patent for the dropout technique. Does that mean you can't do a dropout if you're Not Google? Most likely not valid. Weird. This doesn't describe the problem that I have, which is that, well, maybe it does. Maybe I just have to read this. The one I care about is dropout. So you remove rows from the matrix. I don't know, this doesn't answer the exact question that I have, which is, do you drop out the gradient at the end, or do you have to do it in a different way? Drop out implementation. Maybe this would answer my question if I stopped to read it, but it's just a lot of text and I don't see an obvious answer. Forward propagation equations change in the following way. Is y hat the, where does it explain it? Although, I guess a different thought just occurred to me, which is that if the weights are 0, does that mean my gradient will also be 0? Because we don't like to learn on nodes that are already 0. I'm not sure. For sigmoid, I guess it depends on the activation function even, probably. For sigmoid, your gradient is flat at, no, at 0 your gradient is not, I can't remember. Sigmoid function, what do you look like at 0? Yeah, your gradient is not flat at 0. No, this would be the 0 I'm talking about. So your gradient is flat at 0. So I actually don't even have to worry about zeroing out my gradient if I'm using sigmoid neurons. Okay, let's try this. So I want to pick, this is dropout. Pick a random half of the nodes as to dropout. So what's a good way to do that? So I could think of an easy way to, so that every given node has a 50% chance of being in there, which is not the same as having exactly half of the nodes, but I think it's close enough probably. So the way to do that is to just pick a random number between 0 and number of nodes. And then look at the binary representation of it, and each no, what I want is a number with as many digits, as many binary digits as there are nodes in the network. So that would be a 2 to the n digit number, or a number that goes up to 2 to the n. So 2 to the n. N is self.neurons, so 2 to the wait. That changes in each layer. And I only want to do this in the hidden layers. So let's go here. Give me a random number. How do you do that in Python? Python random number up to rand int, rand range. So yeah, I'm already importing random. Oh, I'm using rand n. No, that's to make a matrix. So random dot rand range. So here's a here's the number whose binary digits represent which neurons should be dropped out. Why doesn't it like this? Oh, because neurons is not what I think it is. How can I tell how many neurons I have? That would be in sizes, which I'm not actually remembering. But I also know that it's the biases, the length, biases is a vector that's number of neurons by 1. So biases dot shape of 0 is the number of neurons. Okay, so now dropout is an encoding of which neurons should be dropped out. Encoding of which neurons should be dropped out. We picked a random number that has as many binary digits as I have neurons. So each one of the digits is 50% chance to be 0, 50% chance to be 1. So now we're just going to multiply our W and our B by dropout base, or by the digits in dropout. So I guess I'm going to call it dropout weights and dropout biases. This is equal to basically it should be a matrix that's the same size as W, and it has a 1 in every row where dropout has a 1 as that digit. Okay, so how do I do that? I'm making a NumPy array. It has dropout shifted to the right by row R, and take this and 1. So if you're a 1, if the digit in that position is a 1, then it's 1. If it was a this is so hard to write and to explain. It'll work, but I think I want to do this in a way that's easier to understand. I think the biases are going to be easier to understand. So np.array, and then the weight is just h stacking the biases. So np.array, you have a dropout R and 1 for R in num neurons. This is making a vector that I then need to reshape. Dot reshape num neurons 1. And then dw is you h stack those. H stack or v stack? I think h stack. db for blank in range num neurons. Also, this needs to be range of num neurons. Okay. Then basically W equals W Hadamard product dW. B equals B Hadamard product dB. And I have no idea if I've done this properly. So let's print dB to start and see what we are getting here. That actually looks good. That's what I wanted it to look like. 30 neurons. I'm guessing there's 30 things here. And it's a column vector. Yeah? Yep. Okay, and it's half zeros and half ones. So dB looks good. How does dW look? And then why don't you print dw.shape also? Yeah, that's also what I expected. 30 by 30. Oh, wait, by 30. 30 is not right because for a few reasons. For one reason. 30 is not right because W is not a num neurons by num neurons large matrix. So this should be range of len of W of 0. Okay, that's doing something now. But it only during the forward propagation is this doing something. But I want to also be dropping out during the backwards propagation. So this W needs to be the same as this W. Okay, so okay, also to do only in hidden layers. There's a lot there's a lot of moving parts here. So here's how I can do this. I need to define my temporary W's and temporary B's they start as self.weights. They start as self.biases. I need them to be copies so I can actually edit them. for, I guess they don't have to start as self.weights and self.biases. They can start as empty lists, then we can set them. So for this, but I don't need the neurons. Let's set the dropout stuff. So do that in here. This is my new W and my new B. So W's dot append this. B's dot append this. Okay. So, and then here, go over the W's and the B's so that you have my new values. And then here, go over the B's. Or wait, I mean the W's obviously. Although this one's the only one that actually matters. Because this is just a number. Okay. Forward propagation. And then backward. All right. Then what am I missing? Nothing. This should be doing dropout now. I mean, at least in the way that I am trying to do it, which might not be the right way to do it. We're overflowing all over the place. Oh, I forgot this, only in hidden layers. So if don't do the last one. Is that what this would be? I guess you can't do that. Can I do it like this? Does that mean don't do the last one? Python 1, 2, 3 sliced at ending at -1. Yeah, it does. And then what if there only were 2? Okay. So I think this works. So don't do the last one, is what this means, which means I have to throw in an extra w's.append self.weights of -1 and b's biases to -1. So I'm saying the last one is not edited. Include all of them, basically. All the neurons in the last layer. Then I think I'm doing what I mean to do. Though I'm not sure if it's going to work yet. I wonder why I'm getting overflows. Because I would think I'm only making stuff smaller, not larger. It's kind of able to learn. But again, it's supposed to be better at learning, not worse. We could try confirming whether whether I am getting zeros in the places that I expect to get zeros in the derivatives. I'm not seeing any zero. Yeah, I'm not seeing any zeros. So maybe I do have to then zero out the stuff I don't want in the end. So here you would do let's just do an extra loop for dropout. For grad W for blank for I in range len of grad W. Grad W of I equals, and then you got to zero out. Oh, I guess that would mean I want to keep these dBs and dWs. Ugh. dBs, dWs. Times dW deltas equals, which is the same as times equals dW deltas times equals dB. What's the issue here? Oh, because this is dWs of I, and this is dBs of I. I don't like this, and I don't even really expect it to work, but let's see if it does. Yeah. Deltas of I. Oh, yeah, you don't want to change the last one. Okay. So it's it's actually possibly working. It's a lot slower because I'm doing all this extra matrix stuff, and it's not better, but we might need to tweak the rest of the hyperparameters. Also, I'm dropping out and regularizing at the same time, and I'm not sure if you're supposed to do that either. So why don't we try doubling the learning rate, since we're only learning half of the stuff at a time anyway. That's not helping very much. What if the learning rate is super high? No, that's no good. Okay, what if we didn't do any regularization? So of like L1 or L2 regularization. So set lambda to 0. No. Okay. So I don't know if I'm doing something wrong or if what am I trying to say? I don't know if I'm doing something wrong with the dropout or if I guess like if I am doing something wrong, it's amazing that it's learning as well as it is, because it's not a huge detriment, right? It's like it's still getting above 90. Anyway, I think we'll put dropout to the side for now. So why don't I copy this guy? I'll paste it in here. Backprop with dropout. And I'll just comment the whole thing. And bring our backpropagation back to the fast version. It's hard to just make it a parameter because I have to make copies of stuff to make it work. Yeah, back to normal. Faster, better. Okay. So yeah, I guess I don't really know what's going on with dropout. I don't know if I did it wrong or if it's supposed to not work that well. Maybe I need more neurons to see an effect. So why don't we try that briefly? So backprop with dropout. Does that work? Yeah. And yeah, it like kind of doesn't work super well. And then if we go back here, and give ourselves 100 neurons, is that going to be enough for dropping out to help? I don't exactly know what I'm comparing to, but maybe I could try doing it without dropout at the same time. Yeah, it works much better without dropout. All right, so I guess I'll leave it there on a bit of a mystery. Again, not sure if I implemented dropout wrong, in which case it's kind of miraculous that it doesn't screw up the learning more. Or if dropout is just not expected to work out with these hyperparameters for whatever reason. But I think that's going to be it for now. Thank you for watching. Hope this was helpful. Peace.